about a nice problem regarding the inertia tensor and the principal axes of inertia of 3 point masses connected in a certain configuration. So I'm going to take out my marker right here, well, several markers actually, and let's draw a configuration of 3 point masses in 3D. So put the cap over here. So what? What? Huh? Closer?
No, it looks funny.
Okay, fine. Break one off. Okay, so don't need dark blue for anything really. I was just adding it for comedic effect. We have over here, bring this back, the X, Y, Z space. And so I'm going to draw 3 point masses. Firstly, I'm going to draw one right over here on the x-axis, 80 units away from the origin. Then I'm going to draw one that was, let's say, 2a on the z-axis and a on the y-axis away from the origin. And finally, I'm going to have a third one that's at the same position on the y-axis, but negative a on the z-axis, which looks like this. Which means that the whole thing's going to end up connecting like a triangle. Nice. Okay, so what I want to do is find the inertia tensor of these 3 connected masses. Imagine that the rods connecting them have no mass. They're magical, just like the pendulums you study in Physics 1. So, how can we find the inertia tensor? Well, normally the inertia tensor looks something like the integral of y squared plus z squared, the integral of, yes, I know, dm, but I'm not going to put that there because we're going to be erasing this in just a second. So this is what. Oh, and let's assign masses to them too. Let's make this m, 2m, 3m. You can see I'm putting a lot of thought into that. So x squared plus z squared and x squared plus y squared. This is minus, this is xy, I think. No. Okay, that's simple. But when we're studying point masses, discrete, not continuous, we don't need to use integrals. We can just use a sum. Since they're point masses, they don't have a density function. We can just write it as the sum from I equals 1 to 3 of mi multiplied by the matrix yi squared plus zi squared, xi squared plus zi squared, and of course integrals are just a generalization of this, where this becomes differential and the number of i's becomes infinite.
Which song is it?
Nothing. Sorry. So you have, this is YZ, I think.
It's like multitasking. You're solving a problem and you're singing.
And then you have minus xi yi and minus xi yi here. Okay, great. So now let's look at the matrices for each one of these points. So the first one is just going to be m multiplied by what? Well, it has no components except x, which means this is 0, 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 and this is 0. Oh, and that's 0. All the products of inertia go to 0. This is a squared, and that is a squared. Pretty simple. Then you have the second one, which is 2m. So it has no x component, which means these 4 products of inertia go to 0. But everything else is pretty standard. you have minus yi times zi, which is equal to, well, minus 2a times a, or minus 2a squared. That's the same over here. Yi squared plus zi squared is just going to be, well, 4a squared plus a squared, which is 5a squared. This one in the middle is going to be xi squared plus zi squared. Xi goes to 0. Zi squared is just a squared. Same thing with this one, but, well, no, not the same thing. This is just yi squared, which makes 4a squared. Okay. And lastly, you have plus 3m. This is mostly the same thing. These four products of inertia go to 0, since there's no x component in the position vector. And the other ones are, well, this is minus a times a, negated again, which gives us a squared here, and then this one right over here is a squared plus a squared, which is 2a squared. Remember, negative signs disappear with squares. Xi squared plus zi squared is just a squared, and xi squared plus yi squared is also a squared. Okay, so you get ma squared multiplied by 0, 0, 0, 1, and 1 here, 10 and 6. So you'll find 16 in the top left. All of these entries are 0 for every single one of these matrices, so we can ignore them. Then what are these four entries? Well, 1 plus 2 plus 3, this one is 6. 0 minus 4 plus 3, this one is minus 1. Same thing over here since it's symmetric. This one is 1 plus 8, 2 times 4, plus 3, which is 12. Which means this is the inertia tensor. Okay, so now let's figure out how to find not just the moment of inertia about an axis, but the principal axes of this, which are the eigenvectors. So, what are the eigenvectors of this matrix? Well, to do that, we first need to find its eigenvalues, which can be found using the equation I multiplied by a vector is equal to lambda multiplied by a vector. Now, the key here is to realize, well, a matrix multiplied by a vector is another vector. So, what happens if that matrix is square? And if that matrix is square, it's going to map this vector to another vector of the exact same size. So, could that vector be proportional to the vector we multiplied it with? Could multiplying by a matrix in effect be the same as multiplying by a scalar in some cases? That's the interesting thing about an eigenvalue. Now, to actually solve it, you realize you can just multiply both sides by the identity matrix. Well, the identity matrix commutes, but I'm still going to move to the other side. So this forms a matrix, just I. This also forms a matrix, lambda, 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 all across the diagonal. Thankfully, determinants are additive, which means we can say that the determinant of IV minus, well, no, the determinant of I minus lambda times the identity has to be equal to 0. So eigenvectors are proportional. Well, what am I saying? Eigenvectors, okay. If we have an eigenvector v1, n times v1 is also going to work as an eigenvector for any given n. That's not 0, hopefully. So that means that as long as this isn't 0, we can just work with this matrix without caring. So what's the determinant of this? Well, it's going to be 16 minus lambda, 6 minus lambda, 12 minus lambda, minus 1, everything else is 0. The determinant of that is going to be what? Well, 16 minus lambda times 6 minus lambda times 12 minus lambda, and hopefully you can tell everything else is 0 except going over this way, this term minus 16 minus lambda is non-zero. Okay, so now we can clearly see one of the eigenvalues is 16, pretty unique. But then, what are the other eigenvalues? Well, we get 6 minus lambda times 12 minus lambda minus 1 has to be equal to 0. 6 minus lambda times 12 minus lambda as well. 72 minus 18 lambda plus lambda squared. Okay, so that gives you lambda squared minus 18 lambda plus 71 is equal to 0. Okay, so now we have to find the solutions to this. So what's the solutions to this? Why did I write x? This should be 18 plus minus the square root of 18 squared is 324 minus 4 times 71 is 284 divided by 2a. So you get 9 plus minus the square root of 10, since this is 4. And of course, the square root of 40 over 2 is the square root of 10. Okay, so now that means you have 3 eigenvalues. 9 plus root 10 and 9 minus root 10 are additional eigenvalues that you can add on. So now we want to see if the eigenvectors, they generate, okay? So to do that, well, we have to solve a system of equations for each one. So let's call our vector v1, so v1 for the first one, v2 for the second one, v3 for the third one. So then we want 16, 6, 12, minus 1, minus 1. We want this to be equal to this. No, I'm not. Okay, so what does that mean? Well, multiplying these two gives us what? 16 vx, 6 vy minus vz, minus vy plus 12 vz. Okay, so that means 16 vx has to be equal to lambda vx, 6 vy minus vz has to be equal to lambda vy, minus vy plus 12 vz has, well, I guess I'll flip it around. 12 vz minus vy is equal to lambda vz. Okay, so that means we can see 16 v1x. Well, what are the solutions to this system of equations? It depends on lambda, of course. If lambda is 16, you get this. So vx could be anything. 6 vy minus vz is 16 vy. 12 vz minus vy is 16 vz. Then it's pretty easy to see.
Maybe go to this one first.
Sure. Fine. From there, it's pretty easy to see that 6 vy minus vz is 16 vy, hence minus vz is 10 vy, vz is minus 10 vy, and 12 vz, wait a sec. Does that constitute a valid solution to this system of equations? 12 vz minus vy is equal to 16 vz, which implies minus vy is equal to 4 vz, which means this one looks like a dud. Vy has to be equal to vz has to be equal to 0 in order for this to work. So let's try the two other.
Can you read one of the comments and answer?
What? No. I'm not completely changing the topic for one comment. Okay. So then we have what else? You have other values of lambda, so you get 16vx is equal to, well, anything other than 16 means vx has to be equal to 0 by necessity. So then you just get 6vy. No, I'm not relying on this. You get 6vy minus vz is equal to lambda vy. No, but doesn't that proclaim only one solution? So that implies vz has to be equal to 6 minus lambda vy, and then vy has to be equal to 12 minus lambda vz, which implies there can only be one solution, because by necessity vy over vz has to be 12 minus lambda, which is equal to 1 over 6 minus lambda, which means that, oh, but there were two possibilities for this to work. Okay, that makes sense. So that means V2 and V3 are not duds. Okay, good. So then all we have to do is set Vy is equal to, well, lambda 2 is 9 plus rad 10, which means 12 minus 9 plus rad 10 is 3 minus rad 10 Vz, which gives what? 0, 1 over 3 minus rad 10. Pretty simple. And I could even rationalize it by writing 3 plus rad 10 divided by I think minus 91.
I have a calculator.
No, that's not what you use when rationalizing something. Okay. Yeah, okay. So you have 0, 1, minus 3 plus rad 10 over 91. Oh, but something doesn't feel right about that. 3 minus rad 10 is way less than 1. So obviously, oh my god, I'm stupid. Just minus 3 plus rad 10. And the other one is where Vy is equal to 12, well, 3 plus rad 10 Vz, where we can expect, well, an eigenvector that looks something like 0, 1, 1 over 3 plus rad 10. But what's 1 over 3 plus rad 10? Well, here's a reminder that 1 is rad 10 minus 3, rad 10 plus 3, which means this is rad 10 minus 3. And this is, of course, minus rad 10 minus 3, which means that these two, which if I had to visualize them on the XYZ plane, they look, well, I could even go back to the whiteboard to do this one. They look something like no X component, just a Y component of 1, and a Z component of minus 10, rad 10 minus 3. It's about minus 6. So I would say something like this. And of course, plus rad 10 minus 3 is about, what can I say, 1/6. Which also means they're orthogonal. So you have two orthogonal principal axes. As you can see, if you dot product them, it will give you 1 minus 1 from this difference of squares, which means that they're perpendicular in their plane. So that's it. Thank you everybody for watching, and we'll see you in the next one. Oh, and I guess I should also mention that these are perpendicular in their plane, and the first eigenvector technically isn't a dud. It just requires Vx is non-zero while Vy and Vz are zero, which means it actually provides a system of 3 all orthogonal principal axes. So that's it. Thank
Now,
you.
some people ask, what is this? Can you explain it, they said, without math for 10 seconds?
No. Okay, so we're going over the moment of inertia. Well, the inertia tensor, which can tell you the moment of inertia, and the principal axes, which are like the stable orientations, or in other words, the points where the moment of inertia are maximized and minimized, and like. They're the stable points of this configuration of point masses. So, essentially, we're finding a tensor that will allow us to find the stable points of a configuration of masses. So, we have 3 orthogonal principal axes. That's it. Thank you everybody for watching, and we'll see you in the next one. If you really think about it, it's like a very thin cylinder. You can only place it in 3 stable configurations. This way, or this way. Yes, technically you can also kind of rotate it, but all 3 of these orientations are perpendicular to one another. So these are the 3 axes where moment of inertia is limited.